All right. So let's get started with the performance measures. This is the second video for the same lecture. All right, so we made the fit in line 73, and we predicted some underscore digit. Remember, their variable from before, which we know is a number 9, right? And it correctly, down here you can't see it, but if you remember from your previous video, you might still have the code open. It gave you a false, because remember, our targets are now just true and falses. It's a binary classifier. We're just testing for whether it's an image of a 5 or it's not an image of a 5. So in this case, this is a 9. It's not an image of a 5. It's false. All right? But hey, that's great. How do we know if this classifier is actually a good classifier? How do we know that the data and the classification that was done is actually gives us good results, right? Gives us good results. Think in terms of, again, regression. You can run regression on anything. It doesn't mean your regression model is actually statistically significant or valid in any way, right? Enter one way to evaluate the model called cross-validation. All right, so what is cross-validation? Cross-validation is when you break up your training data, not the test data. We're not even at the test data part yet, just the training data into what we call k-folds. K-folds, right here, k-folds, right? Slang. For example, when k equals 3, that means 3 folds, or the data will be broken into 3 subsets, right? Then what happens is, hypothetically, let's say we did k equals 3 for k-folds or 3 folds. Then the model is trained and tested k times or 3 times. In each iteration of those 3 times, what happens is, let's go to my Excel sheet. Let's go to the Excel sheet. So here, again, let's make this big. All right. So let's say each box here represents my data, my training data, right? But let's say hypothetically, I now break up my training data into 3 subsets. The way right here, the way cross-validation works is that the training and the testing is done just on those 3 subsets of training data, right? The idea is that each subset takes turns being the test set, while the non-chosen subsets are used to being the train are used to train the model, the classifier. On each iteration, we observe the different measures, right? So what happens is first we create the 3 subsets out of the training data, and then we will measure the accuracy. And then second, we will run the same analysis using the cross-val score. So we're going to do both of this analysis, one by hand and then one using an existing function Scikit-Learn called cross-val score. And again, from a visual point of view, again, imagine this whole yellow box is my training data. If k equals 3, I'm going to divide the box into 3 different sets. And I'm going to run this 3 different times. This analysis now 3 different times. Why 3 different times? Well, because what happens is on the first go, these 2 boxes of data will be used for training the data. And once the classifier is trained on just these 2 sets of data, and it'll be tested on this 3rd set. All right? So let me just make this slightly bigger. So I'll just put make it actually a separate color. Train, and this one will be the test one. All right? So that's one iteration. On the second iteration, what happens is this box and this box data will be used to train the classifier, and then this set right here will be used to test the classifier. And then on the third one, finally, it is this box and this box that are used to train the data, and then this box of data is used to test the data. Okay? Why do we do this? We do this so that if there's any bias in our trading data, this is where it'll come out. This is where it'll come out, right? And obviously you can do k equals 3, k equals 5, k equals 10. If it's k equals 10, then the data we broke it up into 10 subsets, and then 10 iterations would happen in the same kind of logic like we did right here. We want to do k equals 3. And again, we're going to do this manually the first time around, and then we're going to use cross-val score to do it. Easy for us, all right? All right, so first things first, right? We want to create, first of all, we want 3 different subsets, all right? So how do we take our original data set and break our data train training data, and how do we randomly break it up into 3 subsets? We're going to use NP random permutations again, okay? We'll just create another list or vector of random numbers from 0 to 59,999, and then we'll just simply, boom, create 3 different subsets from data train based off on the 3 different positions of those random numbers. So for example, don't be confused here. This is not saying that the first 20,000 will be D train 1. That's not what it's saying. What it's saying is sub all is random numbers. So already it's random numbers from 0 to 59,999. Whatever those first 20,000 of those random numbers are, that's what's going to sub underscore 1. The second set of 20 random numbers is going to subset underscore 2. The third set of those random numbers are going to subset underscore 3. That allows completely randomized subsets from our main training data. All right, let's go ahead and do that. Again, let's see if I can just copy and paste it and fix up whatever needs to be fixed up. All right. Just what you see here, copy and paste, copy and paste. All right, delete that space, and delete that space. Excellent. And we should be ready to rock. I go ahead and run this. Right, and just for kicks, you can't see it right here, but if you were just to do sub underscore 1, just a sanity check and say, okay, give me the first 5 values here, you'll notice you'll get some completely random numbers. Notice the random numbers in your window over here. It's too small for you guys to see, but you guys can see it on your computer, right? And we do the same thing for sub 2 and sub 3, we can do it. Boom, completely different random numbers, and this is what I mean. You have completely different random numbers, right? But each position is unique. Again, down here, completely random numbers. All right, good. From here, now that we have our sub 1, sub 2, sub 3, just like before when we were shuffling the data, just like before when we were shuffling the data here, all right, we were shuffling the data. All right, we put some random numbers in here in the positions. We were doing bracket. It basically turns into bracket comma slicing, and we changed the order. All right, same thing's going to happen here now. All right, it's just that in sub underscore 1, it only has 20,000 values. So D underscore train 1 is now only going to be 20 rows of training data. Same thing with D underscore train 2. Same thing with D underscore train 3, because sub underscore 2 and sub underscore 3 are all length of 20,000. And that's how we took our training data and broke it up randomly into 3 different subsets of training data. All right, so let's go ahead and do that. Excuse me for 1 second. All right, sweet. All right, so we'll call this, I think I call it here D underscore train 1. Try to keep the names consistent. All right, and I simply just put in sub underscore 1. Sub underscore 1 is just a list of numbers, 20,000. Boom. D train 1 is done. And over here you can see 20,000 rows, 784 columns. Now this has 20,000 images. All right, let's go ahead and do the rest of our subsets. Boom. Train 2, train 3, they're there. 20,000, 20,000, 20,000. All the data set is now broken up into randomly subsets. All right, nice. We did this for our training data. We got to do it for our target data, right? And here it is. And again, we have to preserve the order. We have to preserve the order because each training row, each image has its actual value in the training vector. So we have to preserve that order no matter what shuffling or subsetting we do. And this is why directly we're using the same sub_1, sub_2, and sub_3 all over again. In this case, it's going to be this vector is just true and falses, but still we have to keep preserve the order, or the whole analysis will get messed up. Here, just for speed, let me just copy and paste this. Yikes, that's ugly. All right, there we go. So here. All right, here we are. Processes, boom. Look at our target training data. Put down the T's right here. T-train right there. T-train 1. Again, type booleans, 20,000 rows each. Bam, we're done. We're ready to rock. All right. Now the logic here is fairly simple. Now I have my subset, right? Now that I have my subset, I want to go ahead and run the 3 predictions, all right? Now, each time we run 2 of the 3 data sets and test on the third set, we are going to combine the 2 data sets that will be our training data for that particular iteration of the fold. All right. Now, one way to do this is we want to basically stack them up on top of another. We want to make them one. We want to make them one data set. All right. And here's an example. Let's say, for example, I have an A data frame. I'm sorry, A NumPy array and a B NumPy array. Now notice, A is a 2x2 NumPy array. So is B. So I'm sorry, AA, and so is BB. Okay. This is basically meant to be a model of a smaller model of what our actual data set is. Our data set is actually, our training data is 20,000 rows and 784 columns. Here it's just going to be 2 rows and 2 columns. Same thing with BB. But nevertheless, the way we stack it, it's going to be using the append function of NumPy. I'm sorry, AA, BB, and this third parameter, axis equals 0. What axis equals 0 means, hey, it's just basically just take A, stack it on top of B. Boom. Just take A, stack it on top of B. All right, this is A, 1, 2, 3, 4. This is B, 5, 6, 7, 8, and stack it on top of each other. All right, this will be our first subset for our first test set, and then from there we can combine subset 2 and 3 for our first training. For our first training set. All right. So just to keep things easy, the easiest way to do this is let's just, what I'm saying here is when we're doing our analysis, take the first subset as our test set, therefore let's combine 2 and 3. All right, and then for our second iteration, use subset 2 as a test set, so therefore we're going to combine 1 and 3. And then for our last iteration, we'll use subset 3 as a test set, so we'll combine 1 and 2. Okay? So in each iteration, set 1 will be the test set. In the second iteration, it'll be the second one, and the third iteration will be the third set, will be the test sets. So all the other sets will be naturally be the training data. All right, so let's go ahead and do this. All right, first, let's go ahead and get our combined training data for iteration 1. And I'm going to use the npm command right here. Go ahead, let me just go ahead and copy all this. Let me just do it in 2 steps, just so that it becomes manageable. All right, here we go. I'm combining subset 2 and 3 of my training data into a NumPy array called CD1. And right off the bat, you can see, guys, CD1 now is 40,000 rows because we've stacked subset 2 on top of subset 3. Done. All right, now let's get our testing training data. Same concept. Alrighty. NP append, sorry, missing an underscore right there. Without you guys here live, I have to figure out my own errors. All right, and 40,000 right there for our target data. All right, cool, we're ready to go. Now, what's the next step? We're using our SGD, our stochastic gradient descent classifier that we defined from before, to go ahead and fit, to go ahead and train the model. When we use the fit command right there, we're basically training the model. It's taking this training data right here, and it's saying, okay, this training data, these images basically have these values, therefore the model will say, okay, it'll figure out behind the scenes what parameters it needs to set so that these images will give it these values, and that's how the data is trained. And again, later on we can talk about the math behind it. Down here, my right top bottom right window, you guys will see the SGD classifier was called. It gives you a whole bunch of output. It's not really an error again. You do get some future warnings because some things are changing. That's fine. That's more nitty-gritty stuff. But now the model has been trained. Now, what I'm going to do is I'm going to now predict the model is now classified. The model has been now trained. Now I'm going to take my first subset data and I'm going to predict the results from it. I know what the right answers are for dtrain_1. I have them in t_train1. But nevertheless, because I use the other 2 subsets to train this model, I'm going to go ahead and predict it and put my scores, what the values should be, in PRED1. I run this, right? And now I've predicted, using these images, just looking at these images, using my classifier that I already trained on the other 2 data sets, I'm predicting what these images should be, and I put those results right here, predicted 1. And if you just type predict 1 down here in your console, you'll see you'll get a bunch of false truths, right? Which was what we should get, because that's what the target data is. Target data right now is just true and falses. All right, now let's find out how many we got right, people. All right, like I said before, let's find out how many people we got right, and let's figure out what percentage we're accurate. Okay. All right, so number correct. Look at the logic of what I do here, guys. It's all vector logic here. No for loops, no nothing. Basically here I'm saying inside the loop, inside the parentheses, I'm saying, okay, wherever predict1, which is a data container, equals t_train1, which is a data container. They're the same length, so this works. Remember that. Python is not R. When you do this kind of vector logic or vector mathematics, the data containers must be the same dimensions in every way. All right? So here, what ends up happening here is every element, the first element of predict1 is checked to see if it's the same value in t_train1. If it is, that gives us a true. If it's not, that gives us a false. All right? And then it goes to the second element against the second element, third element against the third element, and so on, so on, so forth. Again, I'm doing this without a for loop. All right, now, this is passed into a sum function. What is that all about? These are Booleans, right? Well, the logic here is this. If something is true, right? If something is true, and you pass a bunch of truths in a sum function, a bunch of true and falses in a sum function, what ends up happening is the sum adds up all the truths. So truths basically become a 1, the falses become a 0. So hypothetically, let's say we had 5. Let me just show you this example right here. A real quick example right here. Let's do wad equals 5. Okay. So I have an array, a simple array from 0, 1, 2, 3, 4. And again, simply just type in your wad in the console. You see, unbelievable. I don't want a array. A range. Sorry about that, guys. Right. Type in wad down here. And you see it's an array of 0, 1, 2, 3, 4. Excellent. Now, here, let's do Trump. The guy's all over the news. He's going to get us all killed. Here. Sorry about that. So here now, let's choose, let me do 0. Let me do 2. Let me do 2. Let me do 5. And let me do 4. All right. So basically, only 3 of the values match. Only 3 of the values will match Waj. 0, 2, and 4. So only 3 of those values match the Waj array in those respective positions. All right. So now watch what happens if I do Waj equals Trump. Right? Look at what you get out. You get a output of true, false, and true, right? Because the first elements are the same, the second ones aren't, the third ones are, the fourth ones aren't, the fifth ones are, right? Now, this you guys pretty much should know at this point. This is a little bit new right here. When I do sum on this, it gives me the answer 3. Why? It adds up all the trues as 1s, and all the falses are 0s, right? So that's basically just what happens. Let me go ahead and comment this out, this example. I'll upload this as well, guys. So here, the number that were correct, boom, right there. Now, I'm going to simply just divide the number that were correct by the total amount of predictions. And ladies and gentlemen, this is going to give me a very simple accuracy ratio. How accurate was it? Very simple. How much were correct versus how many total predictions were there? How many out of all the predictions we made, how many were correct? Look at that. Let me copy this. All right. So this go around, I got an answer of 0.96. Wow. That's pretty good, huh? All right, let's do the next one. Let's do it now where the second data set is the training is the second data set is the test data. All right. So I'm going to do everything from before, make my slight changes where I need to make them. All right. So this time, my second data training is going to be a combination of the first training data and the third training data. My test data will be same thing. Sorry. First target training data, third target training data. I'm going to go ahead and refit my model. Again, warnings, that's fine. I'm going to make my new prediction off of what? It's now going to predict that my test data is now my second subset of data. Go ahead and I will run this. All right, now I'll do predict 2 equals 2. All right. Let's call this 2 just so we preserve our original values. All right, and this is 2. I go ahead and do this. 96.13. This is some fantastic accuracy, huh? Huh? A little condensation, a little notice a little sarcasm in my voice. These are good accuracies, right? But obviously, you know there's going to be a twist. All right, now let's do our third one. Oops. And again, our third time around, our training data is going to be the the first set and the second subset. This is because in the third time around, our test data is the third subset. Therefore, our training data is the first and second subset. And now let's fit this bad boy. 3, 3, predict 3. All right. And now we can go ahead and see how this did in terms of predictions. Excellent. 0.9648. All right. Again, great numbers all around. It must be an amazing classifier. All right. Now, from here, let's go ahead and do the same analysis, but this time logically. I mean, look, we went through that whole logic because I'm trying to show you what's going on behind the scenes. But obviously, there's a function for this. It's called cross-val underscore. Cross underscore val underscore score, right? It's obviously much easier. We've imported from this Scikit-Learn model selection underscore model selection, and it basically does exactly what we did, and it gives us 3 results back, right? So let's go ahead and grab this from Scikit-Learn model selection, the cross-val score function, and now you know exactly what this is doing because you just did it. We just wrote it, right? And this is exactly what we just did is happening behind the scenes. Model selection, import cross-val score. This is the name of the function. Import it. And let me just go ahead and grab this. Alrighty. The only weird part here is SGD, that's my stochastic gradient descent classifier model that we declared. I'm giving my data train all of my data, my training data. I'm giving all of my target data, 5, the 5 one. This is, remember, this one is just the true and falses. Now, CV equals 3, what does that mean? K-fold, guys. This means, hey, do it in 3 subsets. If you put 10 in there, it would be do it for 10 subsets, and it'll give you 10 answers versus 3. And obviously, what kind of scoring result do I want back? I want the scoring result for accuracy. Now here, let's make sure it's the right quote. All right. And now when I run this, guys, you'll see, what do I get? I get 3 results. Right there. I get an array of 3 results. Let me just copy that and put that here so you guys can see it. Boom. All right. And as you can see, they're pretty high. They're pretty high. Pretty high. All right, and they're going to be slightly different because remember, when we break it into subsets, we're randomly breaking it into subsets. All right, good, great. So, all right, now these scores are seemingly excellent, aren't they? Remember, I've been sarcastic the whole time, right? And remember, what is accuracy? Accuracy is just number predicted correctly over number of total values. Keep that in mind. That is what accuracy is. It's the number predicted correctly over number of total values. All right? Now, but context matters. I stressed this a lot to you guys when you guys were in ABI, and I stress this again, and I'm stressing this again to my BAP students. All right? Anybody, I can show anybody to type these things into the program. You saw how easy it was to do it. But what does it mean from a business point of view? All right? Context matters. Not only context of the business, but the context of the data that you're using. All right? This is a skewed data set. You have to know that as management. This is skewed, or if you're interfacing with management, this is a skewed data set, meaning that there are some classes that are a lot more frequent than the other. Okay? In our case, there are a lot more non-fives than there are fives in the data set. Okay? This could affect the accuracy. Let's do a test to prove this, right? We'll take our predictions from our k-fold test, and now anywhere where there was a 5 predicted accurately, anywhere there was a accurate prediction, we are going to artificially convert it to a false. We're going to mess with our data, with our output. But we only want to convert it where the true predictions, we only want to convert the true predictions to false, where in the target data the result was true. We don't want to remove the false positives. For example, if you look at this right here in the slide, let's say my target data is false, false, true, false. My predicted data is true, false, true, false. Well, in this case, what's happening here is the predicted data, I want to change wherever the target was true. So see, target over here was false, and I predicted true. I'll leave that. I'm fine with that. I'll leave that. Right? I don't want to get rid of the false positives. Here, this is false. That's false. Again, that's fine. Here, the target is true, and it was predicted true. That is what I want to change. I want to change that value to a false. Right? Why am I doing this? Because I want to make this prediction as horrible as possible. So basically, if there's a false positive, I'm leaving that. See, this is a mistake. I'm leaving it. But wherever it got it right, and the only place it got it right where it was true in the actual value was true, and we predicted true. This part right here, I'm making false. Here it's false. I'll leave it as false. Done. All right. So how do I do that? Aha. How do I do that? And here's a new little thing that I throw in you guys. I explain a little bit more a little bit later because we use this concept again. But this is what's happening here. All right. How do I do this? How do I do it so that so I'm looking at the results of 2 different vectors to make change in another vector. All right. You see what the complexity of what's happening here? Within x predicted, the predicted value, remember, this one I want to change to false. But I want to change it to false where wherever x underscore predicted is true. Yep, that makes sense. And where x underscore target is true. Yeah, it makes sense. And then I'm going to make it false. But at this point, alarms should be going off in your head. You're like, wait a minute. What is going on here? That is correct. Not only within the square brackets am I checking the values for x underscore pred, but I am also checking the values for a completely different array, x underscore target. This will work. Why will this work? 1, they're the same dimensions. That's number 1. 2, this will work because what's happening here is this goes in the same order as this, right? This goes as the same order as this. If we look at this example right here, what happens is this is checked to see if it's true. I'm sorry, we start off with the pred one. This is checked to see if it's true. And then this is checked to see at the same time if it's false. Both conditions are checked. So what happens here, x predict equals true. This is true. X target equals true. Is false equal true? No, that's false. So this becomes true and false. Remember, you need both these conditions to be true. There's an and here. So this doesn't happen. This value, the x predicted value, does not change. Okay? Here, this is false. This whole thing's going to be false. This is false. This whole thing will be false. And again, we didn't have to even check the second one because both conditions were false. That logic keeps flowing through. And it does not until we get to here. X predict, this value iteration, this value of x predict is true. Aha, yes it is. And this one is true as well. Both conditions are true, and now x predict will be set to false. This one will be false. You see, it goes from value position to position in each array. And it does not matter that they're different arrays. it's still going to go in the same order in each of the arrays. And now when we're at the third value, the third position here, we finally have a situation where everything in the conditions is true, and we're finally going to assign the value false to some position in xpred. Well, it's going to be this one. It's going to be this one. Why? Because we're at this point. These are the points that are being tested. These are the points that are true. Therefore, false will only overwrite this point in time in x underscore predict. And that's how we're going to go about. And so this is some funky stuff in terms of logic, but that's how, I have another example like this later on, but that's how we're going to go about, and we're going to change now the x target to be true. Wherever it's, I mean, we're going to change the predicted value to be false wherever we actually predicted it true, right? All right, and that's basically what's happening here with our three predictions. We'll do it in our, we'll go ahead and do it in our the one we did manually, because that we can actually take control of. All right. So here, let me copy and paste all these guys. And again, what we're doing is we're taking all our predicted values, and I'm showing you the absurdity of blindly just following of blindly taking these values. That's giving you, potentially great values, and showing you how ridiculous it all is. Well, it's not all is, but there's more to it than just running these numbers. What just happened? All right, no, let me just do this one by one. That copied so horribly. I'm gonna do this one by one. So let me just do this. Clean that up. Work for us, guys. Take the second part. All right. Just write this up, and I'll explain the logic of this first one right here. All right, here we go. So what's happening here is just like we did before right here, in this example right here. Okay? What I'm doing here is, this example right here, what I'm doing here is, I'm checking wherever my first predictions, my first set of predictions, remember, this is where my my second data set and my third data set were combined to do the training data, and then we tested on the first subset. All right. So basically, I'm saying, look, wherever we have predicted true, all right, and the actual underlying target data was true as well, make those values false, just like we did in our slide. Logically, I'm doing it across the whole vector now. Boom. All right, and I'm going to do this now for my second set of predictions and my third set of predictions. And the third one. Boom. Okay. All right. Now let's go ahead and do the same, knock out the same analysis again like we did before, and get the accuracy. Now, what happened here is, guys, we changed every true prediction that really was true, and we said it was wrong. We made it false. All right. So we should get some horrible, horrible results, right? All right. I should really stop using underscores. Let's do the first one. What is this, guys? Right, remember, we just had, we never predicted 5 correctly. When there was a real 5, we never predicted it correctly. Look at what the accuracy is telling us. 0.89, almost 90%. Ludicrous. Let's do it for the second one. The second one too, almost 89%. %90. 90%. All right. What? What? No, we artificially in lines 128, 129, and 130, we artificially changed our predicted, wherever 5 was predicted correctly, we changed that to false. No 5 was predicted correctly. Then why are we getting accuracies of 89%, 89%, 90%? How is this happening? It's because the data is skewed, right? It's skewed, meaning that there is the 5s are what we call the positive class. The non-5s are the negative classes. But because there's so many more of those negative classes, it's overwhelming the results of the accuracy of this test. All right? And I don't have to tell you, a lot of times you might be dealing with skewed data sets. It goes with the business, right? This is why we use something called a confusion matrix, which is a much better way to evaluate performance classifiers. If you have taken, again, some machine learning class or any kind of analytics class, logistical regression, anything like that, any predictive analytics class before or in this program, you have dealt with confusion matrices. In probabilities, you've dealt with confusion matrices. All right? This is a confusion matrix, basically. For our case, because of the fact that we have a binary classifier and only 2 classes, we will have a 2 by 2 confusion matrix. We had confusion matrix questions on the final in ABI. A lot of you guys did bad on it. So, all right, but here's your second chance at it. The general idea is to count the number of certain one classes and the other class and vice versa, right? For example, our example, we want to see how many times the classifier confused the image of 5s as non-5s, right? And to do that, you would look into the row representing the 5s and the columns representing non-5s. So how is the confusion matrix really set up? The confusion matrix is basically, if you, from this slide and the next one, basically your actuals are your rows, okay? The actuals are the right answer. They're your rows, okay? Your negative class is first, your positive class is second. The predicted numbers, they are the columns. They're the columns. And again, the negative is first and the positive is second. And so how's this being interpreted? The way it's being interpreted is that these amount of images were predicted to be negative, and they actually were negative. So this top cell are all the negatives were predicted. This is what we call true negative. It was predicted accurately. All right. Here, we go here. This is something that was predicted to be a positive class. This was predicted to be 5, but in actuality, it's not a 5. This is what we call a false positive. All right. Coming down here, the second row is all the positive, the actual, the right end, all the positive classes, meaning all the actual 5s. So this cell right here, it actually is 5, but it's predicted to not be 5. This is what we call false negatives. It's being predicted as a negative, but that's not true. It's a false negative. And this cell down here is basically what is actually a 5 and is simultaneously it's being predicted is being predicted accurately. It's being predicted to be 5s. This is what we call true positives. In the previous example, what we did was we changed all our true positives to be false. That's what we did. We messed with all our true positives. and this is a confusion matrix. When you set it up like this, right, you get all these other performance measures that give you a much better, let's say, measure or accuracy or litmus or much better litmus tests to see if your classifier is actually doing a good job doing classification, right? Um, we will go over some of these right now, right? Again, this is basically the formulas for a couple of them. We use accuracy, of course. We use precision, um, or a version of precision. And we use this one here, recall. All right, it's also called sensitivity, right? And basically, just like before, this is how it's broken down. Your actual answers are goes across the rows. Your predicted answers go into the columns, and we break them up into false positives, true positives, false negatives, true negatives, right? And this is obviously for a binary classification problem, and this is why it's 2 by 2. All right. So let's go ahead and build our confusion matrix. All right. First thing we want to do is, again, we have our cross. We want to download this new function right here called cross underscore val underscore predict. Cross underscore val underscore predict. And we're going to go ahead and use that to get our predicted values, whatever our predicted values were. Now, notice, again, my first parameter is SGD, the gradient descent. Just like before, let me go here to my Python code, right? Before, we used cross val score. Now we're using cross val predict. Score. First predict. Score gave us the accuracy, like the actual measurement that we were doing before, that we calculated before. This is not actually giving us prediction. It's literally giving us the true and falses if you want. All right? But again, notice slightly different what's going on here. Here's my classifier. My second parameter, again, is my training data. My third parameter is my training underscore 5 data. And look, my fourth parameter is, again, the CV, C equals 3. So again, it's the k-fold part. This prediction that's happening, it's again happening in the same context of looking at the training data, breaking it up into different subsets, taking those n minus one of those yes, n minus one of those subsets, right, and making a training data out of it, and then testing it on that one subset and doing it over and over again for however many k-folds we have. That same thing is happening again, right? And because of this, we're gonna get a length of what? 60. We're gonna get 60,000. We're getting 60,000 values. Why are we getting 60,000 values? Because the first time, on the first test, right, the first test, we're testing 1/3 of the set, which gives us 20,000 values. On the second round, we're testing 1/3, gives us another 20,000. On the last round, we're testing another 20,000, which gives us a summation of 60,000. 60,000 values, okay? Again, k-fold is happening here. Let's go ahead and download this, and let's run it. All right, let's clean this up. Model selection, cross val predict. Oh, I use the underscore here as well. Might as well go with it. Cross val predict. All right. All right. Train. Did my import. And let's go ahead and get my results. Boom, boom, boom. I got my predictions. If you notice, if I run the len command again, on predict 5, you will see 60,000 values. If you run the np.unique command on predict 5, you will see it's just a bunch of true and falses. All right, cool. So I have my predictions now. I did my predictions now. Before I was getting the scores, now I got my predictions. All right, now from here, let's go and build our covariance matrix. All right, I'm sorry, I'm sorry, I have a typo here. Covariance matrix, confusion matrix, guys. There's a typo here. We're not building a covariance matrix. We're building a confusion matrix. All right. Now, here, guys, I'm just gonna, again, it's all done for me. I'm gonna go import the confusion matrix function from Scikit-Learn, right? This is the beauty of Scikit-Learn, guys. It has everything. It has everything right there for you to use. Confusion matrix. All right, now look, check this out. All right, the first parameter of your confusion matrix is what? Sorry, this should be underscore. The first parameter of your confusion matrix function is what? It's my actual target results, the right answers. Remember, the right, true, and false answers are in target underscore train underscore 5. Okay? Predict underscore 5 are my predicted values. So here we go. I run this. Oh, sorry. I didn't run the first part. Ah. All right, I got my confusion matrix. Now I can go ahead and run this. Boom. You see these results I have right here. So these are the results I have right here. Let me copy and paste this. Let's see if you can see it better here. Excellent. All right. Now we talked about this. What are these results saying? Now here, let's see how off it is from here. 5, 3, 4, 2, 2. Okay. It's slightly off. So my numbers I get here are going to be slightly different than numbers I have here. So just be cognizant of that, the numbers I have here versus the numbers I have in my slides, and your numbers are going to be slightly different as well. Okay? So what's happening here? Okay? Like we said before, the first row are your falses. So basically your false class. So in our case, the actual non-5s. The second row are the positive classes, the actual positive classes, so the actual 5s. The first column is your predicted falses, so whatever's predicted to be not a 5. And my second column is actually predicted to be positive, so my actual predicted 5s. All right, so here in my slide, basically, 53,722 were actually not 5, and they were predicted accurately to not be 5. 4,000 were actually 4,000 were actually predicted to be 5 accurately. All right. 1,421 of the 5s were not predicted to be 5s accurately, and 857 of non-5s were predicted to be 5s. All right. Same thing is happening here. All right. 53,433 were actually not in the 5, and they were actually accurately not predicted to be 5s, whereas 1,146 also were not 5, but they were predicted to be 5s. All right, down here, 1,244 were predicted to be 5s, where they were again they were actually 5, and they're actually 5 here. All these run here. This row right here is the actual 5s. But these amount were predicted to be non-5s, and these were accurately predicted to be 5s. So that's basically how your confusion matrix works. That's basically what it's saying at that point. Now that we have this box, right? Let me comment this out. Now that we have this, we can calculate some of those performance measures from our previous from slide number 28. All right, from slide 28. All right, so let's start partying. All right, let's look at two performance measures that usually tend to go side by side. All right, so precision. What is precision? Precision is your true positives divided by your true positives plus your false positives. What is recall? Recall is your true positives divided by your true positives and your false negatives. Those are the formulas, but what do they mean? All right, now, hypothetically, let's assume that our confusion matrix, our classifier was perfect. If our classifier was perfect, you will see that the actual 5s over here were predicted to be non-5s. okay? And our actual 5s were all predicted to be 5s, right? In this situation, what's your precision going to be? Your precision would be your true positive, right there, divided by your true positive over your false positive, okay? All right? I'm sorry, your true positive over your true positive plus your false positive. What's your false positive here? Your false positives are the ones that are predicted to be 5, but in actuality are not 5. All right, so what's predicted to be 5, but in actuality are not 5. Okay? So in here, what's our false positive? If you go to the previous slide, right, where are your false positives? Right up here, guys, the top corner. They're predicted to be 5, but in actuality they're not 5. This part, it's 0. So what ends up happening is 5 over 2, 1 plus divided by 5 over 2, 5 over 2, 1 plus 0 over 5, 4, 2, 1 gives me a precision of what? Precision of what? It gives me a precision of 1 or 100%. Now let's look at recall. What is recall? Recall is true positive. Again, what is true positive? Same numerator, whatever is predicted to be 5, which is actually 5, divided by your true positive, again 5421, plus now what? Your false negative. What's your false negative? All right, what's your false negative? It's something that was predicted to be negative that's actually positive, or actually, so whatever is predicted to be uh, false was predicted to be a non-5, but was actually a 5. In that case, again, it's 0. So this also will give us 5421 divided by 5421, and our recall would be 1. So a perfect classification will give you a precision of 1 and a recall of 1. Now, precision is basically the accuracy of the positive predictions of a certain class. All right? It's the accuracy of the positive predictions of a certain class. Right? For example, for the ones that were predicted 5, how many were actually 5? That's what precision is saying. For the ones that were predicted 5, out of the ones that were predicted to be 5, how many were actually 5? That's precision. All right, now, here for our actual matrix, 5's precision was what? 4,000 divided by 4,000 plus 857, right? Your true positives divided by your false positives, okay? That gives us 5 precision of 0.82. Okay, an accuracy of 0.82, precision, sorry, of 0.82. This is the 82% accuracy of the images that were predicted to be 5. Predicted to be, so this is an accuracy of 82% that were predicted to be 5. So basically, the images of 5, according to this classifier, the classifier we trained, it tends to find the 5s 82% of the time, all right? Which is now lower than our previous measure. That is actually lower than when we artificially altered our classifier to be messed up. It's actually lower than that, right? So now we get a little more true reality of what's going on here. All right. Now, what about the images that I ask you? Okay, so this is telling you, okay, cool. And by the way, for the non-5's precision, if you notice, it's very high again, 0.97. But again, remember, this is skewed. There are a lot of non-5's out there, right? There are a lot of non-5's out there. So you have to be contextual with that. You have to take into context that. Now, okay, that's great. Precision is basically telling you for the pictures you predicted to be 5, 82% of them were 5. Fantastic. Okay, now, what about the images that were 5, but they weren't predicted to be 5? What about that? Huh? That is what we call recall. And that is why recall is used in conjunction with precision to help measure the performance of a classifier. All right? Recall, which is also called sensitivity or true positive or the true positive rate, TPR, is the ratio of the positive instances that are correctly detected by the classifier. All right? Again, mathematically, let's go over it and then I'll show you an example of what it really means. So here's our data again. again, this my data here is slightly different than the one I have here from my actual the one I'm doing along with you guys, and it's obviously going to be a little bit different than the one you guys are doing yourselves. All right, but here we go again. Your actual recall is again your true positives, boom, plus your false negatives. All right, boom. I calculate this, and I have a recall of 0.74. Ah, what's going on there? From the classifier, we see that the images of fives that are found correctly, they're only found correctly 74% of the time. What that 0.74 means now is that out of all the fives, all right, out of all the fives in our makeshift testing data, remember we're doing K full 3, right? We're actually testing within the training data itself. But out of all the test data, 74% of the time we found the fives, meaning 26% of the time we didn't. There are fives we didn't find. All right. Now, how do we actually get these scores? Again, we see these scores. We can do it manually. I obviously want to show you guys how you can do this in Python as well. We have actual functions for that as well. Like I said before, Sklearn has functions for everything. It's fantastic in that regard. So for my and yours analysis we're doing, let's get our precision score and let's get our recall score. Now again, notice I'm using, in a second, process this. Okay, let me do this. Actually, let me get, if I can get both of them, let me grab both of them. Perfect. All right, a white. All right. So here, now notice this precision score. I'm giving the target train data again and whatever I predicted, and it's going to go ahead and crank the precision score just like we did here. Whatever we did manually here for precision, I'm sorry, this is recall, for recall and precision right here. All right, these functions are going to do. All right, and again, I'm showing you what's happening behind the scenes, but obviously in actuality we would use these functions. So here, so for the data that I'm following along, that I'm doing along with you guys, I have a precision of this. Wow, wow, 78%. All right, and I have a recall of this. All right, 77%. All right, and again, please remember you're interfacing with management. You're solving business problems with this. What that precision score says is that out of the fives we found, out of the fives that our program found, 78% of them were actually fives. And what this is saying, from a business point of view again, out of the all the fives in the actual data set, only 77% of the time we found the fives. All right? That's what it's saying. Precision and recall, side by side. All right, now notice that we have, again, both the precision and recall. Now, there's another measurement out there called F1 score, the F1 score, which is what is in math, it's called a harmonic mean, right? And for any of my math students, you're going to recognize this. You're like, oh, yeah, harmonic mean, right? And this is a great example for how we use mathematics in making business decisions. A fantastic example, all right? So harmonic mean is a concept in mathematics, right? And the formula obviously is down here. But what it does is a harmonic mean, unlike a normal mean, right? So let's say we wanted a single measure that combined both the precision and recall to give us some sort of score for a classifier, right? Well, instead of taking the average, the simple the arithmetic math I'm sorry, the Euclidean mean, the normal mean that we always the normal mean you always tend to use, which is the Euclidean mean. If we don't take the normal mean, right, of if we just took the normal mean of precision and recall, right? We would get a simple mean. I'll show you that in a second, and we'll crank that out. We'll get a normal mean, right? But the F1 score is not a normal mean. It's a harmonic mean, right? Now, what a harmonic mean does, it gives more weight to lower values, and as a result, a classifier can only get a high score if both numbers are high. That's what's so clever about harmonic mean. And again, in finance, we use tricks like this all in quantitative finance. We use tricks like this all the time, right? Using these mathematical tricks like here. So why would we want to do that, right? Why would we want to do that? We want to do that because if we have one score representing both precision and recall, first of all, you saw from before that the objective here is to have a precision recall that are both 100%. That is a perfect classifier, right? Anything that was predicted to be positive was positive, and all the positives were found. Perfect, 100 score, right? So in a F1 score and in a normal mean, the average of a mean, the average of two ones is 1, and in F1 score, the average of the two ones are 200% is actually 100% as well. The difference here is that if one of the either precision or recall is slightly smaller, right, is slightly smaller, in a normal mean, your average will be slightly smaller as well, right? But not so with the F1 score. The F1 score is sneaky in the sense, in the mathematical sense, that it applies more weight, right? It's not 50% recall, 50% precision. It applies more weight to the number that is smaller, thereby making that mean a whole lot smaller than it otherwise would be, right? And that's why the F1 score is effective as a measurement for both the precision and recall. All right. So obviously we have a function for that. Sklearn right here. Import F1 score. Stick your target data and your predicted data, and then you're going to get the results. But what's happening behind the scenes mathematically, right? This is the formula for F1 score right here. 2 divided by 1 over precision plus 1 over recall. Or whatever numbers you're taking. Whatever numbers, hypothetically, you're taking the F1 score for. It doesn't have to be just precision and recall. I mean, for example, in quantitative finance, let's say we're scoring the ROC and the earnings yield. These are just ratios, financial ratios in the investing world. If I wanted to have a combined score of them, I could use the same harmonic mean model right here. So here, notice that if precision and recall were both 1, right, then F1 score would just give you an answer of 100%, easy, right? But now notice that if any of these numbers, first of all, this formula turns into this formula right here, which basically simplifies it to this formula, right? Because we break down precision and recall according to their true positives and false negatives, et cetera, et cetera. But very simply, notice that if any of these numbers starts becoming small, mathematically you can see it's going to have a different effect on F1. It's going to have a different effect of F1. So here's your formula right there. If we go ahead, I don't break it down mathematically for you, but obviously you guys know you're going to get something like this on the practice set, right? So here, let me find out what my F1 score is. Hold on a second. All right, excellent. I just want to make sure I had a practical example for you guys to digest this a little more. This could get a little confusing. F1 score, excellent. Boom. All right, so I imported it and I ran F1 score. Again, my first parameter is my actual result, the right answers, and this is my predicted answers. Right, and as you can see, I get a score of 0.77, right? And obviously that's because a lot of these, both my scores from up here, they're around 0.77. It's going to be 0.77. All right, so 0.77, that's my F1 score. It's okay, right? It's all right. Is that good? Is that bad? Again, it's in the context of the business you're doing. All right, let's talk about that. All right, when do you want one over the other? Right? When do you want one over the other? Um, When it comes to precision and recall, you're going to see in the next slide, there is a trade-off between precision and recall, always, right? When you don't have a perfect classifier, In this case, right, when you're training a classifier to detect videos that are safe for kids, right, safe for children, what do you think do you want? Do you want more precision or do you want more recall? All right. When you're searching for videos that are safe for children, the precision must be very, very high, right? We don't really care about recall as much as we do precision. Why? Because what we're saying is this video, we predicted that this video, think of YouTube. We predict that this video is safe for children. Okay. If that's the case, if you predict that this video is safe for children, then in this context where you have some sort of algorithm or website that just only has kid-friendly videos, you better have an extremely high precision. If your classifier is predicting that this video is safe for children, it better be safe for children. If one video comes out that's not safe for children, your business is tanked. All right? You're probably going to get fired. All right? You're probably going to get fired. So that precision, you're sacrificing everything for that precision, right? And here we are fine sacrificing recall for a high precision. Why? Because what recall is saying is that, oh, you know what? For all the safe, friendly videos out there in YouTube, we might be getting only 60% of them or 50% of them. That's okay. There's a lot of videos out there. I don't need them all. What I do need is the ones I do say are child friendly, are child friendly. I am completely fine by missing out on the other 50%, hell, 70% of videos out there. What I want is the videos my model does find, and I do post on my website to make my money, is indeed child friendly. That is an example of where we want high precision, and we're willing to sacrifice all the recall in the world for that. All right. Now let's look at the flip side. Training a classifier to detect shoplifters on videos. All right. Now, here, this gets kind of hazy because you can have potential lawsuits here, but hypothetically, like in high-end places, high-end jewelers, high-end clothing, they don't give a damn, right? They don't give a damn because I mean there are stores out there. I'm sure some of you have been there where scarves are like $1,000. Little leather wallets are like a couple hundred to $1,000, right? Purses I don't have to tell you guys they go up to $10,000, $20,000, right? They don't mess around in these places. Okay, they do not mess around in these places. All right. So in these cases, we have video cameras. When you're digitally detecting, your video camera is digitally detecting? Is it better to have high recall and the precision or is it better to have higher precision? So in other words, would you rather have higher recall for the sake of precision, or would you rather have high precision for the sake of recall? In this situation, right, you want a massively high recall and you are willing to sacrifice precision. Now remember, again, I have to be contextual here. This is only for the high-end stores. The high-end stores don't really care about if they're perceived to be biased in any way, if you guys know what I'm talking about. All right, my MBA students will know what I'm talking about here, right? But in these high-end stores, they don't care because this really will affect their inventory, right? If a shopper is incorrectly, so what does high recall in this context mean? Well, high recall in this context means is that anybody that is a shoplifter, we find to be a shoplifter. And if you're doing this, what happens is your precision will suffer. That there are situations where you will predict somebody to be a shoplifter, and they might not be a shoplifter, right? Your precision might go down to 50%, where it's a flip of a coin whether the person that your algorithm classified to be shoplifting was actually shoplifting. But in this situation, it's okay. You want that high recall. Because in this situation, if there is a shoplifter, you want whatever number of shoplifters you have, you want to make sure you get them all. It's very important you get them all. Because also in the world of thievery, right, what happens is if a store is a mark, usually when somebody, steals something, everybody knows it's been stolen and spreads along it could spread in the thievery community, if you will, right? I'm not talking about amateurs. I'm talking about like people that are a little more professionals, high-end grifters. it'll spread. That look, you can steal from this place, right? So it's very important for anybody that actually is a shoplifter according to the video camera is identified to be a shoplifter, right? And here you will sacrifice precision. You will take the embarrassment. That is fine. You'll probably give them a in these high-end stores. You apologize, and they have these little knick-knack gifts they give as a way to say, "Oh, I'm sorry." All right. So, but this is a great example, again, especially for my MBAs, of machine learning and these measurements and the trade-off between these measurements in play, in action. All right. Now, the trade-off. How does the trade-off actually work, right? Does the SGD classifier, the stochastic gradient descent classifier, how does it make the distinction? Well, all right. So this lecture is already around an hour and 15 minutes. You know what? This is probably going a little bit longer. I want to try to keep these videos to an hour and 20 minutes. I don't want to go above hour and 20 minutes. So, you know, at this point, I'll end at slide 34, and I'll pick up I guess, the next part at slide 36. But for class, you only have to worry up to, looks like up to slide 35. Some of you might be seeing that I have 64 slides here now. Yeah, I'll update this. At Blackboard, I'll put the new updated version of Lab 5, and you guys can take a look at it. So I'll end this video at this point, up to slide 34. And the next part will pick up at slide 35, and we'll go onward from there. Now, for class, I mean, for the WebEx at this point, if your code works fine and you understand all the material, there's no questions, you don't have to log in at our different hours. So again, I have class on Tuesday night tonight, actually Tuesday night, Wednesday afternoon, and Sunday morning. If you do have a question or you have something wrong with your code, please log in and we'll work through it. All right, I'll send out the link on WebEx shortly, and you guys will have it. For my Tuesday evening class, I don't know if you're gonna be able to watch the videos, especially since some of you guys are telecommuting right now, working online. If you're gonna be able to see the videos by 6:40, if you are, I'll be there, and if you have any questions, I'll be there. If not, please look at the videos, and then for you guys, because you know you guys have less time, go ahead and log in on Wednesday afternoon, or if Sunday morning works best for you, then log in Sunday morning. And again, you only have to log in, guys. The classes now, what's going to happen is these YouTube videos are served as our classes, and the WebEx time during our normal class time is now going to serve as basically office hours for me to help you. Because again, when it comes to these programming classes and these math classes, there's a lot of, it's one thing to learn things online, right? But you might have some questions, so I want to make sure I have plenty of time online on the WebEx to give you guys opportunities to answer those questions. All right, so this ends this video, and keep a lookout now for my soon part C to this. I'll put up soon. All right, thank you guys.